When we look at the elements of the symmetric group in one-line notation as permutations, it's pretty clear that the identity element is the one that has the letters 1 through n all in order. We could say all of the other permutations have the letters not in order. But also, if we look at them closely, we could see that some of those other permutations are pretty close to being the identity, pretty close to having the letters in order, and some of them are pretty far from having the letters in order. So it can be useful to measure how out of order the letters in a permutation are, to say how close to the identity it is or how far from the identity is. There are a couple different ways to do this. So we can think of this as measuring how scrambled or far from in order a permutation is. There are many ways to do this, in fact. One way is to count inversions. An inversion is a pair of letters ji with j greater than I, but appearing earlier. Right, so if all the letters were in order, there wouldn't be any inversions. Then the more out of order they are, the more pairs there are where the larger letter appears before the smaller letter. So for example, let's look at the permutation 5, 2, 6, 4, 1, 3, 7. To count inversions, we could look at each letter and say how many things to the right of it are smaller than it. So the number of letters, well, let's just list the letters that are to right and smaller and then count them. So we've got 2. So we've got 5, 2 is an inversion, 5, 4. 5, 6 is in the right order because 5 is smaller. Then 5, 1, 5, 3. So we've got 4 letters that are to the right of 5 and smaller. 2, there's only one letter that's to the right of 2 and smaller than it. That's 1. So 2, 1 is an inversion. That adds 1 to our count. 6 has 4, 1, and 3 to the right of it and smaller, so that adds 6. That adds 3 to our inversion count. 4 has 1 and 3 that are to the right of it and smaller, so that adds 2 to our inversion count. Then 1 doesn't have anything to the right and smaller, 3 doesn't, and 7 doesn't either. So the number is 4 plus 1 plus 3 plus 2, which is 5 plus 5, which is 10. So we write INV of 5, 2, 6, 4, 1, 3, 7. Number of inversions in this permutation is 10. So number of inversions in 1, 2, 3, 4 up to n always is 0 for all n. And then the number of inversions in the completely descending permutation is n choose 2, because every single pair of letters is out of order. Now actually let's Let's do this for all the permutations in S3 as an example. So we have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So this has 0 inversions, this has 3 greater than 2, this has 2 greater than 1. Here we've got 2 greater than 1 and 3 greater than 1, so there's 2 inversions. 3 greater than 1 and 3 greater than 2, that's 2 inversions. And here we've got all possible inversions. 3 is greater than 2 and 1, and then 2 is greater than 1, so there's 3 inversions. Now this word that we made that records how many letters are to the right and smaller is called the code of the permutation. So there's 0 things to the right of 1 and smaller, 0 to the right of 2 and smaller, 0 to the right of 3 and smaller. So that code is 0, 0, 0. Here the code is 0, 1, 0. Here the code is 1, 0, 0. Here the code is 1, 1, 0. Here the code is 2, 0, 0. And here the code is 2, 1, 0. I think we talked about code before. So the components of the code add up to the number of inversions. Another way to measure what's out of order in a permutation is when we have a large letter immediately followed by a small letter. So we call I a descent of the permutation W1 through Wn if Wi is greater than Wi plus 1. So for example, if we look at the same permutation from before, well, let's call DSW as the number of descents. So if we look at the example from before, 5, 2, 6, 4, 1, 3, 7, it's standard to write a bar between a greater letter and an immediately following small letter. So 5 is greater than 2, 6 is greater than 4, 4 is greater than 1. So we can see there's 3 descents here. And sometimes it's interesting to remember exactly where the descents are. So we might use capital D of 5, 2, 6, 4, 1, 3, 7 to be the actual positions where they're descent. So that's position 1, position 3, and position 4. Now descents and inversions are different because 5, 4 counts as an inversion because 5 is greater than 4 and comes earlier, but it's not a descent because we only count inversions that are adjacent. Greater letter followed immediately by smaller letter. So the number of descents is always going to be less than or equal to the number of inversions in a permutation. And I guess we can use S3 to practice computing descents. So 3 is bigger than 2, 2 is bigger than 1, 3 is bigger than 1, 3 is bigger than 1, 3 is bigger than 2, 2 is bigger than 1. So the number of descents is 0, 1, 1, 1, 1, 2. Again, descents of W is always less than or equal to number of inversions. Another way of measuring how out of order a permutation is the length of the shortest possible product of generators. For the permutation. So for example, I can use the same chart here. So it doesn't take any generators to make the identity permutation. But here, if we swap S3 and S2, that's the generator S2. And if we swap the first and second letters, that's the generator S1. And then these two permutations I think are S1, S2, and S2, S1. Let's see. S1, S2 of 1, 2, 3 is S1 of 1, 3, 2, which is 3, 1, 2. So this one is S1, S2, and then S2, S1 of 1, 2, 3 is S2 of 2, 1, 3, which is 2, 3, 1. So S2, S1. And then this one is S1, S2, S1. And that expression by the braid relation is the same as S2, S1, S2. The expressions are different, but they refer to the same permutation. So the length is 0, 1, 1, 2, 2, 3. And it turns out those are the same numbers we got when we computed inversions in each of these permutations. And it turns out that number of inversions in W is equal to the length of W always. So the shortest number of generators that it takes to get a permutation is equal to the number of letters that are out of order. So to prove this, let's show two different inequalities. First, that this number is less than or equal to the second one, and then that the second number is less than or equal to the first one. Therefore, they'll have to be equal. So let's show first that number of inversions is less than or equal to length. So let's start with the word 1, 2, 3 up to n. And let's apply let's suppose that SI1 through SIK is a reduced expression, and by reduced I mean shortest possible, for some permutation W1 through Wn belonging to the nth symmetric group. So applying SI1 through SIK to the word 1 through N, SIK first and then SIK minus 1, etc., working from right to left. Now every time we apply a generator to this word, we're going to switch two letters. We could be switching letters that are in order and putting them out of order, or we could be switching letters that are out of order and then putting them in order. But whatever we do, if this is a reduced expression, we're going to end up with at most k pairs of letters out of order, because at worst we could put things out of order at every step. One pair of letters out of order, one pair of letters out of order. At every step, at worst, we take one pair of new letters and put them out of order. So we introduce at most one new inversion at each step. Possibly we introduce fewer inversions. So that means that the number of inversions we end up with can't be any greater than the length, the number of generators. Alright, so we're claiming that number of inversions in W equals length of W. Okay, so we've established that inequality. Now let's look at the other inequality. So for n equals 1 and 2, this is true. In fact, we have equality. Because the first symmetric group consists of just the single word in one letter, which has length 0, and the number of inversions has to be 0 because there aren't two letters which could possibly be out of order. The second symmetric group consists of the words 1, 2, and 2, 1, where 2, 1 is the generator little s1. So the length of 1, 2 is 0, which is the number of inversions. And the length of 2, 1 is 1, because we can express it just as one generator. And the number of inversions is also 1, because we've got 2 before 1, and that's it. Now we've already established one equality, so if we assume that we have the other inequality for symmetric groups capital S1 through capital Sn, we're really assuming that we have equality for capital S1 through capital Sn. So let's assume we have number of inversions greater than or equal to length in the symmetric groups. I think I'm going to use n minus 1 for my assumption here. So capital S1 through capital Sn minus 1. That is because we proved the other direction of the proof first. We have number of inversions in W equals length of W in the symmetric groups capital S1 through capital Sn minus 1. Now let's consider W, which has n letters and is in the nth symmetric group. And let's suppose that the letter N appears in position P. So let's just keep this down here. We're claiming that inversions is greater than or equal to length. So if the letter N appears in position P, we have WP equals N. Now let's let W prime equal W with N removed. So W prime is a permutation Sn minus 1. So by our inductive assumption, we have number of inversions in W prime equals the length of W prime. And the number of inversions of W is this number plus however many numbers are to the right of N and smaller than it. So the number of letters to the right of N and smaller. So we're assuming we put N back where it was in position P. So this is number of inversions in W prime plus, I guess there's N minus P things to its right that are smaller than it, because all of the letters in that word are smaller than it, and there's N minus P of them to the right. What if we like L of W prime plus N minus P? Alright, so we have an expression for the number of inversions in W. Now how about an expression for W in generators? Now an expression for W now, I'm not claiming this is necessarily the shortest. Is whatever expression we could find for W prime so any expression for W prime with now I'm picturing the word W prime with an N on the end. So Sn minus 1, Sn minus 2, up to Sn minus P on the left. Because W equals W prime. So we can take W prime and put N on the end with N moved over N minus P places. So we start with this and move N over one place and then another place, and then we keep moving it over until it gets into position P, And that would be one way to get the word W. So if SI1 through SIK is an expression for W prime, then little s n minus p dot 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 up to little s n minus 1 si1 through sik is an expression for W. Now this expression has length k plus n minus p, and k, if we start with if we assume this is a reduced expression for W prime, then we've got number of inversions in W prime plus n minus p. So since W prime is in the n minus first symmetric group, we can choose this expression for it, so this is reduced. Let me put reduced here. Of course, even if it weren't reduced, this would give us an expression for W. But let's assume it's reduced so that then we can see how long our expression for W is. So this expression has length of the reduced expression for W prime plus n minus p. But that is precisely the number of inversions in W. Now, we didn't say that this was the shortest possible expression for W, but if we found one expression for W that's this length, then the shortest possible must be less than or equal to that. So this is one expression for W. So that means that length of W equals length of shortest possible expression for W must be less than or equal to number of inversions in W. So we just proved the other direction of the claim, and now that we've got both inequalities, then we have the equality of number of inversions in W and length of W. The end.